Hi everyone! In this video we're going to move on to our next set of nucleophiles, our nitrogen nucleophiles. So let's start with primary amines. And let's say that we have an aldehyde reacting with our primary amine. So remember that a primary amine has a nitrogen bonded to an alkyl group and two hydrogens. The reaction medium should also have a somewhat specific pH value. So we are going to use a buffer that has a pH between 4 and 5. So that just ensures that the reaction works. So the products we end up with, we get something called an imine. So it sounds very similar to amine, but we've replaced that A with an I. And just notice in particular the carbon-nitrogen double bond. And then our other product is a water molecule. So we could very easily reverse this reaction using Le Chatelier's principle. So if we add stress to the product side, equilibrium will move towards the left in order to alleviate that stress. So we could add more water, and that would push the reaction back towards reactants. So this is reversible. Now let's look at the mechanism for this reaction. So the lone pair on nitrogen is going to attack the carbonyl carbon, pushing electrons up to oxygen. So we'll end up with a negatively charged oxygen atom there, and then nitrogen is still bonded to the two hydrogens and the alkyl group, so it's positively charged. Now, similar to our oxygen nucleophile mechanisms that we saw last time, in the next step, we're going to transfer one of these protons on nitrogen over to oxygen. So what we'll do is we'll just write plus minus H plus in brackets. So that tells us we're just removing the proton and then adding it back on somewhere else. Okay, so now the nitrogen is neutral. It's only bonded to one hydrogen and an alkyl group. And then our oxygen is now bonded to a hydrogen. So it is also neutral. Now, in this next step, we're actually going to protonate that oxygen, and we'll just use acid from our buffer. And that's going to create a good leaving group. Okay, so now we need to move our lone pair of electrons from nitrogen down to create a double bond, and that's going to cause our leaving group to leave. Already drawn the wrong thing. Let's see. So now we have a double bond to nitrogen. So this is starting to look like our product. Now in this very last step, we're just going to remove that hydrogen from nitrogen. And we can just write minus H plus here. Okay. So pretty similar to some of our oxygen nucleophile mechanisms that we saw last time. Now, what if we have a secondary amine instead of a primary amine? So a secondary amine has a nitrogen that's bonded to two alkyl groups and a hydrogen. And in this reaction, we're again using that buffer. And this time our product is going to look a little different from the imine. So we're just going to have a single bond from carbon to nitrogen. And nitrogen will still be bonded to its two alkyl groups. And then we have a double bond from the what used to be the carbonyl carbon to its alkyl group. And then the hydrogen from the aldehyde. Let me just make that double bond a little more distinct. There we go. And our other product again is water. So this is also a reversible reaction. We could add water to go back to the reactants. And this is called an enamine product here. Oh, and the key component here is the En there. So remember last quarter we talked about enols, which had an alkene and an alcohol in the same molecule. Here we have an alkene and an amine in the same molecule, so we call it an enamine. So the En is due to the alkene. So let's look at the reaction mechanism for our secondary amine. So similar to the last mechanism, our lone pair on nitrogen comes in and attacks the carbonyl carbon, and then we move our electrons up to oxygen. So now we have a negatively charged oxygen, and then a positively charged nitrogen. Now in the next step, again, we're going to move that hydrogen over to oxygen. And here's where we add our acid, not water. And again, the oxygen is going to grab onto that proton to create a good leaving group. Okay. And similar to our mechanism from earlier, the lone pair on nitrogen is going to move down to create a double bond, and that will kick out our leaving group. Okay, so now we have a double bond to nitrogen. And let's say our alkyl group for the carbon below is a methyl group. And we're just going to draw out that methyl group. Because in the next step, what we're going to do is use one of our water molecules from solution and perform elimination. So water can come in and take one of the hydrogens from carbon. The shared electrons get left behind as a double bond. And then the pi electrons between carbon and nitrogen are going to move up to nitrogen. All right. So then we get our final product. All right, so now that we've gone over these mechanisms, let's do a practice problem. I'm going to give you a ketone this time, and I'm going to give you an actual amine, not just a generic one. So this amine has 2 ethyl groups and a hydrogen. Again, we're going to use that same buffer. I'll just put an asterisk next to it. And I want you to try to figure out what is the product or products for this reaction. There might be a couple. So feel free to pause the video, try this on your own first, and then we'll go over it together. Okay, so let's go back to our mechanism here, since we know we have a secondary amine. So looking at our final product, we know that we'll have our nitrogen up above with its 2 alkyl groups, and down below we'll have a double bond and our other group. So let's draw nitrogen, and in this case nitrogen is bonded to 2 ethyl groups. Okay, and then we have a double bond down below, but that's also on an ethyl group. And then we'll still have our other ethyl group that's going to remain all singly bonded. Okay, let's see. Are there any other products in this reaction? Well, we did say that water was a product, right? But looking at our double bond, is there a different way that we could have formed that double bond, or a different type of alkene we might have formed? So remember, double bonds can exist as either cis or trans, right? So we could have just as easily formed this product. So now let's try to assign E and Z to these 2 double bonds. I said cis and trans earlier, but if you look at the double bond, you'll notice that there are 3 different groups attached. So we have to use E or Z to describe the double bond. So see if you can assign E and Z to those products. All right, so the first one would be a Z configuration because the 2 higher priority groups are on the same side. So they're both pointing kind of up. And the other product would be E because the higher priority groups are pointing in opposite directions. Oh, and I forgot a carbon on my E configuration. So what is the relationship between these 2 products? Are they constitutional isomers, enantiomers, diastereomers, or are they the same? So we can already rule out identical. We know they're not the same because we said that they're, Z and E isomers. Let's see. Do they have any stereocenters? No, it doesn't look like it. So that rules out enantiomers and let's see, constitutional isomers, right? Everything's bonded in the same place. But remember, cis and trans alkenes are considered diastereomers, even though they don't have any stereocenters, right? So Z and E also counts. Those would be considered diastereomers. I know it's been a while since we've talked about all these different types of isomers, so this is a good refresher. Now, because these 2 are diastereomers, we can easily separate them due to their different physical properties. So let's just write that we can easily separate due to different physical properties. Okay. Now, there are some other nitrogen nucleophiles that we could potentially use depending on what type of product we're trying to form. So let's say we have a ketone and we react it with something called hydroxyamine. So this is an amine where our alkyl group is actually an alcohol group or a hydroxy group. And we're still going to use that same buffer that we were using previously. And this forms something called oxamine. And we won't go through the mechanism. It's pretty much the same as before. Oh, whoops, sorry, I spelled oxamine wrong. It's oxamine. All right, and then there's another nucleophile we could use as well called hydrazine. So if we use that same buffer, we end up forming something called hydrazone. So hydrazone is very flammable, so you have to be careful with this. Okay, now one really cool thing about that hydrazone or the imine that we formed there, we can actually easily reduce it. So that reduction is called a Wolff-Kishner reduction. So Wolff and Kishner were the two scientists that worked on this reaction. So it's Ludwig Wolff and N.M. Kishner, if I'm pronouncing that correctly. So let's see. Let's actually go back and review our Clemmensen reduction that we saw in our previous chapter. So remember, if you have a ketone bonded to a benzene ring or even an aldehyde, you can use an amalgamation of zinc and mercury with hydrochloric acid, and that will reduce the ketone to a simple alkyl group. So kind of similarly here, but slightly different, our Wolff-Kishner reduction involves the reduction of an imine. So let's say we have a ketone like this one, and let's add that hydrazine to it. Using that buffer again. So we'll form our intermediate, which is an imine. So we have that carbon-nitrogen double bond. But this is also called hydrazone because we have that NH2 group coming off of the nitrogen. So many names for so many things. But what we can do is add potassium hydroxide and water as well as some heat, and we can form cyclohexane. So that imine group just comes right off essentially. I mean, really we're replacing it with two hydrogens, right? Since we're reducing it. But as a result, we also produce nitrogen gas. So that would bubble out of solution. Okay, so let's look at the mechanism for this reaction. So we'll just start with our hydrazone or imine and work from there. Actually, let me draw the full structure here. Okay, so again, we're adding potassium hydroxide, but potassium is just a spectator ion. The important part is the hydroxide. So that base is going to grab one of the hydrogens that's on our imine. The electrons will be left behind as a double bond. So that means that our pi electrons are going to end up on the top carbon on our ring. So now that double bond has moved to the two nitrogens. And now our carbon on the ring is negatively charged. We also are going to use water, and that's just to protonate the carbon on the ring. So I'll just draw that hydrogen in that we added to that carbon. And next, so now hydroxide is going to come in again, and that's going to grab the hydrogen on the very end of our nitrogen chain there, and then the electrons that are shared will be moved over to create a triple bond. And then the shared electrons between nitrogen and carbon, they're just going to go down to carbon. So kind of strange, but what we end up with is a negatively charged cyclohexane ring. We also have our nitrogen gas and water. So our negatively charged carbon on the cyclohexane ring, that's going to grab a proton from water. And I'm not drawing the full mechanism there, but you know what that is. And we get cyclohexane plus nitrogen gas plus our hydroxide, which will regenerate from our water molecule that just lost a proton to cyclohexane. Okay. So hopefully this kind of helps with all those nitrogen mechanisms. Again, if you wanted to, for instance, end up with just that alkyl group or those alkyl groups on your ketone, and you want to get rid of the carbonyl on it, you could first convert it into a imine or, an imine, and then you can add base, water, and heat to reduce it. And just kind of get rid of everything that's attached to those alkyl groups. Now in this case we used a ring, but you could also use a chain as well. That should work too. Okay, so we'll stop there today, and next time we're going to cover our other nucleophiles, like our sulfur nucleophiles, carbon nucleophiles, and hydrogen nucleophiles. So I will see you then.